All right. So thank you all very much for being here and deciding to listen to me yammer on about stuff. I appreciate it. And more to the point, hope it's interesting. We have about, so first and foremost, my name's Rob. I have been asked to repeat the questions if you have a quick one. I will happily answer questions if you have a quick question. And otherwise, there'll be a mic going around afterwards. Other housekeeping, this is roughly, I think, 28 slides in a 50-minute thing. It's going to go rather quick. There's a lot of content. That being said, it is meant to give you a, hey, look, this is a thing, also all the way through. There'll be an agenda, like a, here's what we're going to cover. I just wanted to be clear about, there'll be a lot of content. The slide deck will be made available afterwards. So if you're interested in this, you can find that information later. All right, let's just jump in then. So we're going to go over why would I bother doing this? Like, what are we doing? Existing alternatives and why they don't fit. We're going to go over Fuse, Elixir and the Beam, consensus algorithms, Raft, and a demo, and then questions. That's a lot to cover, and to be very blunt, it's a high-level overview to get to the putting it all together. So for the few people in the room, and honestly most of you, distributed operating system using Raft as a consensus mechanism, using Elixir with Fuse. That's what I did, and that's what this talk is about. So, getting a little bit more into it, what's the point? Why do this? Most people here have a few servers. Most people have servers that probably talk to other servers. I happen to run servers that talk to each other and are geographically distributed, and I wanted them to have the same state. And we'll go over there are many ways to do this with no problem. But at the end of the day, I am getting a little bit of feedback. It'd be nice if that could be turned down just slightly, but it's not the end of the world. Hey, that's great if you could do that. Awesome. Okay, I'm glad I asked. Anyway, so I'm running a small Anycast system. There you go. I needed to keep state. I did it a few different ways, but this is about using Raft. That's what I'm solving for. One out of three. Alternatively, take your pick. If you run quorum, you can run, 2 out of 5, let's say. But I'm solving for basic quorum. And the idea is that the machine could go down, and then it could come back up at some later time, and I could recover from that. And while that machine is down, everything else keeps ticking along. So it ensures the files, and this is a file system again, right? So you can do this with a bunch of different things down to a file system. No single point of failure. All nodes have the same software and roles. This is a big one because you can solve this with many different ways. I wanted a solution that I could deploy one-to-many in terms of a configuration and in terms of like my software bundle, let's just say. Has to work on OpenBSD, and I don't have any serious performance concerns with this system. So by that I mean I'm not doing a serious heavy read or write. Raft as a consensus algorithm dictates that you have one reader and one writer at one time. That's how it guarantees consistency. So there are other systems that don't do that, but you are basically, with this system, sacrificing performance for reliability and availability within certain constraints. And yeah, so single writer is fine. Offhandedly, those are some of the existing alternatives. So first and foremost, run S3FS and MinIO, or take your pick of whatever else you want, like Ceph or distributed file system. That would be what most people reach for. That's what I reached for. It doesn't work with OpenBSD because of the Fuse version. And one thing I've taken away from this was that I should have just got my hands dirty and bumped the Fuse version that was available, because it would have been a lot easier than doing what I did. You can also do a change of architecture. So with OpenBSD, pretty standard stuff to run pairs, right? So carp, and you could use iSCSI or block stuff to do pairs and NFS over that. People are running kube on OpenBSD by way of like a VM, right? So putting a single core and then running Linux on that. You could do that and it would work. I didn't want to do that. And then the crazy thing that I did that I talked about earlier at a different conference was basically block iSCSI devices, block software RAID, carp, and NFS to get the same functionality. But that resulted in a lot of complexity and a fairly high chain of stack, and more to the point, the machines were different. The machines didn't have the same roles at that point. It becomes really painful if you have different disk layouts. Yeah, would not recommend. Don't do that. So we're going to rip through this really quick. So pace is going to be picked up. File system in Userspace allows for programs to define file systems. Those are some of the things it does, etc. Basically, you interact with the file system, and there'll be a diagram next, and it goes into your program. Your program decides what happens. It's fairly flexible, and it's not as performant. You're going down and back up on the kernel, right? So it's not as performant. Go figure. That's what it looks like. That's probably more useful to most people in the room than the slide before it. Basically, down and up. Your application hits something, and your application defines file system. Different applications, that is. On OpenBSD, was added in 5.4. It is Fuse version 2.6, and there's also, it's worth mentioning, if you get into this, Fuse has two different versions. It has a kernel ABI version, and it has a public version that it talks about. Those are not easy to separate. But the bottom line is there are some things and packages that already exist that use Fuse. So SSHFS, exFAT, and UnionFS does what it says on the tin. And the one thing I would look to note is UnionFS is kind of neat because it does it based on directory, not based on anything else. And so you can do stuff like, have a remote NFS mount and actually do UnionFS on top of that, so that you can actually do your storage is over there. But if you can use mix and match. Bottom line is, though, if you look at other operating systems, the list of packages for Fuse are much, much larger because of the Fuse version. And that's just simply nobody's had time to look at that and do it. And there hasn't been a demand, presumably. I should have done that. Oh, good. I did actually put that in. We're going to go really quick through this. There's a lot of stuff about Erlang and OTP and Elixir. This is a stack. There's going to be a diagram on the next slide to give you an idea. If you're not familiar with Elixir and Erlang, it is an ecosystem that's really nice, comes out of Ericsson a long time ago. It's adopted by a bunch of different things now. And I'm not going to go through all of these points, but the basic idea is you've got a stack similar if you don't understand or don't care. It's not the same, and there are people who are going to really care, but for a high-level overview position, if you're familiar with Java, there you go. There are things that are packaged up along with a VM, and it is a VM. It does have bytecode, that kind of thing. Yeah. So, and Erlang and Elixir are the languages. They do have Lisp in there as well. The big thing here is kind of the overview. So you've got a stack, and your applications run on the top. And in the Beam and these languages, you have a lot of processes on top. So you can easily have tens of thousands, hundreds of thousands, millions of processes that are Erlang or Elixir processes that live on top of that language. And so those would handle things like a single HTTP request, let's say, is a very common use case, or a single TCP stream would have a process dedicated to one particular stream. For our purposes, package add Elixir. That's really high level, but that's really basically it. It gives you the entire stack, and then you can write programs. There's a thing, I really wish there was a diagram I could find on this. I didn't have time to, I didn't prioritize putting a diagram here. That ecosystem has an idea of ports and NIFs. And ports are, as they say, separate processes, and they communicate standard in, standard out. So it's a way of saying, it's basically the foreign function interface. Let's just say that. It's not correct, but it's close. You can run arbitrary programs as a port, and then talk over standard in, standard out to that program. And you can't crash the beam easily. And that's important because basically the Elixir and OTP stack are designed to handle failure gracefully. All of these processes I was talking about at the top, the whole point, well, not the whole point, but one of the major points is that you can actually have one of those processes crash and the entire thing doesn't crash. This, using ports, allows you to, if your port crashes, it doesn't crash the beam. And so for certain workloads, that really matters. NIFs are compiled and linked in, and they're more performant because of that. You don't have to go through that channel, but you can crash the beam. And because of the synchronous communication on there, you can actually, there's a whole bunch of, as you can imagine, you've got, say, 10,000 processes way up the stack in this VM. There's a scheduler that exists in that massive stack I'm not going to go into. That scheduler is really important because it actually makes sure that all the stuff up there works, right? If you write an if, you can starve the scheduler, you can do some bad stuff, and you can crash the thing in a few different ways. Okay, say it with me. Consensus algorithms are not discovery mechanisms. They might include them, but they are not the same thing. It's a very, very, very common misconception. So just right off the bat, this is not about how nodes find each other. This is not about how systems discover each other. This is consensus algorithms that I'm going to be talking about are about how do you come to an agreement. So, I'm going to do it on time. Not too bad. You can read, hopefully, if you can't, there are some screen dictation software things, but the high levels of this slide are, this is not going to be a deep dive into consensus algorithms. The things that you need to care about is, do you need to handle Byzantine fault? So an actor that is not doing what they should. So if you have 3 nodes, if one of them goes rogue, do you care? Are your systems set up to detect that? That Raft, as an algorithm, is not. It assumes that all of your nodes are acting fairly and properly. You may need to care about this. There's a bunch of different algorithms. Paxos down there is a pretty common one. We'll go into it with one slide. Raft, I think, has 3 slides, and there's one slide about crypto and DHTs just to kind of set them aside. So to get that out of the way, because it's a thing, if you Google consensus or you search for consensus algorithm now, you are going to get a lot of results relating to blockchains and DHTs and crypto. It is the same thing in some ways, but it has distinctions. Most of the time they're dealing with public chains, so they're trying to solve problems that are, if you have anybody in the world being able to talk to this or talk to each other, and we want to agree on something, how do you do it? That is the same problem in a way as what I'm trying to solve for, but it's really not, because you end up with, I have 3 nodes, not thousands or hundreds of thousands, and I generally speaking trust them. So there are different algorithms to do different things. Yeah, and they have different properties. There's the FLP proof. If you're interested in this, by all means, take a deep dive. Consensus algorithms basically comes down to you have to have some trade-offs. You can't have everything. So in an ACE, the point out of this slide is if you have to have a system, a consensus algorithm has to be designed in a way that can take, assuming that it's asynchronous, it has to have certain properties. Because if it's synchronous, you're all in lockstep, that's fine. If you're async, you don't know if this node has gone bad or it's down, versus it's just taken some time. And so you can't reach finality or termination. You have to put some bounds on the thing to be able to, you have to loop it, basically. You have to have an iterative process. Or you can also just live with the eventual consistency. So in this terminology, eventual consistency is basically, think of it like dirty reads. You can have a system that has 3 nodes, the writer changes one of them, and you read it immediately and you get the previous version. That would be eventual consistency. Paxos, yeah, lots of stuff there. Tried and true, used all over the place. Big notable ones for this crowd are probably Ceph. It's used a few other places as well. And the original paper is really only a single decision. So there are many variants specifically to handle this. And one of the big things we'll see with Raft was to replace this. Replace being a very, not real replacement. They do different things, but in different ways. Okay. Raft. It's designed to be, and we are going to get to this whole actual file system, I swear. It's just, I'm setting you up with all the steps, right? So we went over Elixir and that stuff. We went over, some consensus algorithms. We went over Fuse. We'll put it all together and we'll be in good shape. So it's designed to be easy to understand. That's, if you haven't looked at Raft, if you don't have experience with consensus algorithms, Raft is the one that is approachable. It's taught in universities these days a lot. Paxos and Raft are the main standards. Paxos being the standard that gets taught traditionally, Raft in the last 10 years or so. It is a strong leader, as I mentioned before. So what that means is not only is it not BZT or Byzantine fault tolerant. It also, at one point in time, there is one leader. And if that leader goes offline or dies, there are mechanisms that we'll get into very shortly to replace that leader. But when that leader is the leader, when that node is the leader, it is in charge of determining things, which makes reasoning about dynamic systems fairly straightforward. Because you can say, okay, well, at this time this was the case. You have one source of truth, sort of. We'll get into the consensus algorithm itself, but you have one source at one time of truth, unlike a distributed system that you can make Paxos into, where you have many, many, many decisions going on at the same time, and those decisions can be spread across different nodes, which is really good for performance in some ways. It also adds a lot of complications. So I mentioned it has guaranteed consistency. That's where that strong leader comes in. So writes are directed to that one leader. And then that one leader communicates out to other nodes. There are some things there. Reads can be dirty depending on your implementation of Raft, but the default one is that they go to the leader as well. So if you get a read in from a local machine, it'll go, well, I'm not the leader, but I will forward that request over, and then goes, yep, it's the same. So you end up with consistency guaranteed because of that, but you end up with performance issues as a result. It's also on the slide. It's very popular. You are probably running it, almost guaranteed. So it's in Kube because of etcd. It's in Rabbit, Kafka, ClickHouse. The Hashi stack runs it, so Consul, Nomad, all that stuff. It is very popular for a reason, because it trades off performance and a lot of performance really, for understandability. And that's attractive when you're dealing with certain types of systems, or systems that you want to be able to maintain. It is worthwhile mentioning that Raft is designed to handle, your application has to handle certain things, right? So like, yeah, there are properties of it that you have to take into account. I'm gonna do it on time. Yeah, 1:30, okay. That's the basic overview. We have a log and a state machine. So clients, as in your program, talk to Raft, internal to Raft, which is that described as that server there. There is a log, and it's append only is the logic. It's not technically append only everywhere, but it's append only on the master, or not the master. Terminology is pain in the ass, coming from different places, but from the leader. When there's agreement on that log between different machines, and agreement being majority, then it gets applied, and that change gets applied to a state machine. Your reads come out of that state machine. So this is all a very fancy way of saying you have a replicated state machine that has some guarantees. So that if you talk to it, you have a replicated state machine, you have that state that's guaranteed. That's what it looks like, very roughly speaking. So you have 3 states that a node can be in, or a member can be in. Fairly straightforward in the sense that a follower is a follower. It just takes in information and goes, yep, that looks good, basically. There's also I haven't heard from the leader in a long time. I need to maybe become the leader. Candidate in that process, and then a leader. That's it. It's not that complicated compared to many, many other systems. Last few notes on Raft. So there needs to be compacting of logs. So that slide previous, we had this notion of logs, and then those logs get pushed into a state machine. Well, if you run a system for a while, the log's going to grow to infinity. You need to have some way to agree to shrink those back down. That's a thing. I didn't touch on the details, but Raft has a notion of terms. So basically, a term is related to the leader. So there is one leader per term. And the way in which the Raft algorithm works, roughly speaking, is that if a leader fails, or is perceived to have failed by a majority of the cluster will agree on a new term. And that's the way in which you can ensure that everybody's on the same page. There are 2 or 3 RPCs. There are more if you want to, but the paper goes into 2 in the basic paper. It adds install snapshot for 3 otherwise. But the RPCs for the nodes are not too bad. Cool. So now that we got that, we got Khepri. Oh, I swear we're getting there. I designed this in a roundabout fashion to get to the stuff that's fuse. Replicated on disk library for Elixir. Raft is used by the RabbitMQ systems. For a storage mechanism, RabbitMQ usually uses, for stateful queues, it uses an application that's built into Elixir. And that is really nice, but it also has some problems from a eventual consistency perspective. So what I'm referring to is if one node fails or you lose quorum with the cluster of them, the system that comes with the OTP and Beam and Elixir and technically it's ERTS, but it exposes that problem back up to you. So you have to deal with it as your application. So like you want to handle, oh, there's a consistency issue here. That has some annoyances, let's just say. Khepri has Raft basically currently available. And so this is actually related to Rabbit. So RabbitMQ, you can use Khepri right now as a storage system, just behind a feature flag. And the biggest thing as to why Khepri is a pain in the ass right now and why I'm not using it all over the place, although it still is quite nice, is that it stores its contents in memory as well, right now. So not a big file system right now. There you go. There's some more stuff about Khepri. It's really good. Highly recommend you look at it. It comes out of Broadcom and VMware and RabbitMQ. But you can change some stuff with it, and there are some details there. It ends up with a tree structure. You have puts, gets, deletes, and transactions, and triggers. So I was at a different conference, and somebody was talking about injecting certain files or hooks where if somebody scanned your system, it tripped an alarm. You could do that with this because a trigger or a stored procedure is just an anonymous function or a piece of code that runs when something gets accessed or something happens. So that's an application for this as well. So I am way early. I ripped through this, which is good. So it's current, yeah. Pulling it all together, we've got 3 nodes. Each one runs Elixir application in the same code. That is a big piece of why I did this. There are other solutions to this, right? They can find each other. I'm not going to go into tons of detail, but for me, I just went, okay, I've got 3 nodes. They're not going to change that often. I'm just going to push that configuration out to those 3 nodes. You can do that dynamically, obviously, to find each other. Khepri gets started. A C program starts as a child from Elixir, and then it calls fuse main, which is inside the port, as in the C program that gets compiled. It calls fuse, and there you go. So single port based package. So in this ecosystem, there was one package that already existed with Fuse. It's called eFuse and UserFS. They were not mature, and they were Linux specific. I had to not just modify the makefile and include paths and that kind of stuff. I actually had to fix the code as of yesterday. I was like, why is this blowing up now? No, they had a buffer overread. So yeah, also had to implement a lot of the calls. So thank you for the people who maintain ktrace and kdump, because that was useful. I did create a Fuse NIF, and I didn't actually end up using it. It uses Rustler, which is basically, because there's a massive ecosystem of Elixir systems, Elixir has NIFs. If you're bothering to do that, there's some reason why you're adding in code to the Beam specifically. You want those things to be safe. And so there are some packages that exist that try and put guardrails around that. Rustler is one of them. It basically makes it very, very nice and easy if you have some Rust code to have it run in Elixir and call it back and forth. So you can go, oh, I want to call this Rust function. And you can do that back and forth. All with nice macros. And it also handles all the type conversion for you. I ran out of time on that, so I started to make it work. All right, so there's the demo. I have a YouTube video, or like a video as a backup, but we're going to do this hopefully live. Yeah, good. So let's see. Let's just load up this. So I have an OpenBSD system here. It has a Fuse file system on it. So what's actually running is, yeah. Oh, even with that, it's noticeable. Yeah. Thank you. Yeah, exactly. Okay, we'll make that nice and big. So on this machine, you've got the beam. It's running. It's running as root because you have to for certain things, as in to spawn a process that then ends up being able to do the thing. That should change. It also should change because that program right here, this one, that efuse, should actually drop permissions as soon as it gets run. That isn't done yet because I had to make it work. But the basic idea is you end up with that. It defines a fuse file system, and that fuse file system interacts like a normal file, right? If I go to a different machine, it's also mounted here. It's a different machine, different city, and it's also there, right? So these files have basic, file D. If you try and do something on this that isn't implemented in your fuse file system, it will blow up at you and not let you do it. You can also, this is because the port and or the program that is running Fuse doesn't implement that, and so it'll kick back an error. This also means, oh, I'm sorry to the people on the stream because I just touched that mic. It also means that you end up with weird metadata because you can implement git adder. So the program is in charge of all of this. So you can make it do whatever you want at any point, which is great, but it means that you can default to certain things. So you'll notice it's all, epoch 1. So it's also worth mentioning the write path is not actually, you notice I couldn't write to this directory? That's because the write path isn't defined in that one package. And I made the assumption before I submitted this talk that, oh, that's there, good, I'll do this. I solved my problem with another way, see aforementioned NFS and block IO scariness. So for this purposes, I ended up with a write path that is just this. So this is going to one machine. Let's go here. So Khepri is basically, I can run a command and get all of the stuff in star. It's also worth mentioning that, so I was talking to somebody about this earlier, it's worth mentioning that for performance and using Raft, people usually shard the heck out of it. By that I mean you will have a Raft cluster, you have multiple Raft clusters. And so that could be by directory or it could be by file for this purpose, but you would end up so that you have multiple masters or multiple leaders just for different clusters. And so you end up being able to say, oh, well, you don't have a contention on the read and write because that gets distributed. I am running a single Raft cluster, mainly for simplicity and making it work and going, hey, look, this is kind of neat. So Khepri up here on one node, this is called Vulture 1. It gives me that. Same thing will happen if I do it over here, right? Straightforward enough. I set up, if I do a Khepri that, there's now an entry here that is just foo and bar. And if I were to, now look, there's now foo. And it has bar. And on another machine, it's the same thing. Go figure. That's it. There's 3 machines. They all have it. And when I said that write right there, I also have a simple web interface to do that. But that's just the write path because I had to implement something to make it work. But the bigger thing is I can shut this down. Now it's going to complain at me because of that. This is still working, right? And the members are there. There are 3 nodes, so it's happy. So the write path still works. So I can do stuff like this where I do, I put foo2 in there. It took it because it still has cluster, still has quorum, even though one of them's down. I can turn this back on. Imagine that just came up. And it'll spew a bunch of stuff. And now, because I did it this way, you'll see an interesting thing. This is still mounted, but that process no longer exists that it's talking to. So now there's an interesting thing where I do this. You get that. So this is a discrepancy of fuse file systems where you end up with the file system doesn't exist anymore, even though it just came back up, because I shut down the program that was running the fuse system. So there are some edge cases here that are a pain. So you do that, kill that, start it again, and now that'll come back. And we end up with, once that comes back up, it's there. And if I were to that, we now have those two files. And that server was down at the time of the writing. Right? No. With the content. So that's the basic idea. Yeah, I don't think there was much more, because it was really just like, hey, look, use a file system is a thing, one slide. I would rewrite this thing in like this Elixir port. It was brutal to work with. I had to add a write path, obviously, so you can just like interact with the file system on the right side to then have it propagate to all other ones. There's a bunch of security stuff, right? It's worth mentioning, there's some really good work on the separation of Beam instances. On the FreeBSD side, people have gone through, DCH has gone through and done Capsicum, so you can run multiple instances and then have, say, one root that needs it for the fuse stuff, let's say, if you need to. But then you can have your other applications not have that permission. Yeah, I'd use RA instead of Khepri, and I would actually use the existing file system. So, yeah, question?
About the multiple Beam instances.
Yeah,
Is
I will repeat it.
You'll have to repeat.
Yeah.
Is Beam one of those apps where like you can only have one per system namespace? Like, is that why Capsicum is required in order to separate them?
Sure. So the question was, is Beam a system where you can only have one instance per namespace, and whether or not that was required because of whether or not how it interacts with Capsicum, very roughly speaking.
Capsicum, FreeBSD has like the whole namespaces thing, but OpenBSD doesn't.
Right. Yeah, so the mention was FreeBSD has Capsicum, OpenBSD doesn't. The Beam can be spread multiple times. You can specify an instance name, and those are completely separated. They have different, they're different processes from the OS perspective, and they have different scratch spaces, and they have different identifiers. And so on the FreeBSD side, you can start multiples of them and use Capsicum to do that. On OpenBSD, you'd end up immediately dropping into pledge. And I wrote a small little package that allows you to call pledge from within Elixir, but that applies to the entire instance. So you'd end up having to do that, the entire instance of the Beam, or the stack. So you'd end up starting multiples and doing the same thing. One thing I would like to point out very briefly as I start to wrap up, which is timing not too bad. Any questions or concerns and heckles, and we're done like a little bit early, which is good. I was hoping to actually use the actual file system instead of using Khepri. So Khepri uses, if I were to take a look at my storage right here, so the files that exist in this directory, let's just say, the contents of those files and the metadata about them lives in a directory, and this is just the default naming. You can obviously name it whatever you want, but it lives in a directory that is internal to that system. So I can't go to somewhere and go like, oh, I want to cat, the file or whatever else. Because it's a fused file system, there's nothing saying I couldn't, instead of using Khepri, or even use Khepri and change out the back end, but that's a complicated thing. So probably just use RA or like a Raft cluster and write that to a separate directory. So you end up with two directories on each node, one of which is HA'd and guaranteed consistent, one of which you can do dirty reads from. And if you write to it, it's a problem. But you would end up being able to have that offline. So that's one thing that I wouldn't mind to have done. Yeah, and out of all of this, I would bump the Fuse version. That's on my list of things to do. That's the number one thing, is all of this could have been solved by just bumping the Fuse version, because I wanted a distributed file system. And so I need to buckle up and learn to do that. That's it. Questions, comments, concerns? I'll go over anything else. So crickets. That's really good or really bad? Hopefully bad. Okay, well, thanks. Give you back your time.